Look up at the night sky, and what do you see? A vast, unchanging sea of stars. Right, but here's the truth. It's all an illusion. The universe isn't static. It's stretching, expanding in every direction, like an inflating balloon or a loaf of cosmic bread rising in the oven. Right now, galaxies are racing away from us at speeds so immense, even light struggles to keep up. And the craziest part, the farther you look, the faster they're moving. This isn't science fiction, it's the mind-bending reality of our cosmos. A reality that challenges everything we thought we knew about space, time, and our place in the grand scheme of things. Picture this: the fabric of space itself is being pulled apart, carrying galaxies along for the ride. It's as if the universe is a rubber sheet, and some invisible hand is tugging at its edges, stretching it further and further. But who or what is doing the pulling? That's one of the greatest mysteries in modern science. For decades, astronomers have been piecing together clues, measuring the expansion rate of the universe with ever-increasing precision, only to uncover more questions than answers. Why is the expansion speeding up? What unseen force is driving it? And what does this mean for the ultimate fate of everything? Our planet, our galaxy, even time itself. That's exactly what we're diving into today. Over the next few minutes, we'll uncover 30 astonishing facts about the expansion rate of the universe, facts that will twist your perception of reality. From the echoes of the Big Bang to the mysterious dark energy pushing galaxies apart at ever-increasing speeds, we'll explore how this cosmic stretch affects everything from the tiniest particles to the largest structures in existence. So buckle up. This journey isn't just about distant stars and far-off galaxies, it's about understanding the very nature of the cosmos we call home. And trust me, by the time we're done, you'll never look at the night sky the same way again. In the early 20th century, most scientists believed the universe was static, an unchanging, eternal backdrop of stars. Even Albert Einstein, the genius behind relativity, was convinced space was unmoving, tweaking his equations to preserve this idea. Then came Edwin Hubble, an astronomer whose groundbreaking observations would shatter that belief forever. In 1929, while peering through the massive 100-inch Hooker telescope at Mount Wilson Observatory, Hubble noticed something extraordinary. The light from distant galaxies wasn't just dimmer, it was shifted toward the red end of the spectrum. This redshift wasn't a small detail. It was a cosmic scream, proof those galaxies were racing away from us. The farther away a galaxy was, the faster it seemed to flee. The universe wasn't standing still. It was stretching, growing, like an unstoppable tide carrying everything with it. Hubble's discovery led to the Hubble constant, a number representing how fast the universe expands. Imagine it as a cosmic speedometer. For every 3.26 million light-years a galaxy is from us, it moves away an extra 70 kilometers per second. That might sound abstract, but this single number rewrote our understanding of reality. It proved Einstein wrong, forcing him to abandon his cosmological constant and later call it his greatest blunder. What's even wilder, Hubble's telescope, the most advanced of its time, was primitive by today's standards. He worked with photographic plates, manually comparing star positions to track motion. No computers, no digital sensors, just patience, precision, and a mind bold enough to question the cosmos. His work didn't just change astronomy, it revealed a universe in motion, setting the stage for the Big Bang theory and everything we've learned since about the expansion of space itself. The universe isn't just expanding, it's stretching from within, transforming space itself in a way that defies everyday intuition. Think of it like a balloon covered in tiny dots, each representing a galaxy. As you inflate the balloon, every dot moves away from every other dot, not because the dots are traveling across the surface, but because the rubber itself is stretching. That's the essence of metric expansion. Space isn't a static stage where galaxies move, it's the stage that's growing, carrying galaxies along like passengers on an invisible cosmic raft. This analogy helps explain why distant galaxies appear to rush away faster than nearby ones, just as dots near the balloon's surface spread apart more dramatically than those close together. Galaxies billions of light years from us recede at mind-boggling speeds simply because there's more expanding space between us and them. It's not that they're speeding through space, it's that the space between us is multiplying. But here's where the balloon analogy gets eerie. Unlike the balloon's surface, the universe has no center. No matter where you stand in the cosmos, every other galaxy would seem to be fleeing from you, the same way every dot on the balloon sees the others retreating. It's a cosmic illusion of perspective, proof that expansion isn't about galaxies racing outward from a single point. It's about the very fabric of reality stretching uniformly everywhere at once. And just like a balloon's rubber grows thinner as it expands, the universe's energy density drops over time. Gravity once fought this expansion, slowing it down, but something mysterious took over, dark energy accelerating the stretch against all expectations. Imagine blowing up that balloon only for it to suddenly inflate faster on its own, defying the air you're pumping in. That's the enigma astronomers grapple with today. This stretching fabric concept reshapes how we perceive distance too. Light from ancient galaxies travels across expanding space, its wavelength elongating into redshift like a cosmic fingerprint of stretching spacetime. Even as you watch the night sky, the universe continues to grow, silently weaving new space between the stars. The balloon isn't just inflating, it's doing so at an ever-increasing pace, rewriting the rules of cosmic destiny with every passing moment. Light doesn't lie. When it reaches us from distant galaxies, it carries a hidden message, a cosmic fingerprint encoded in its color. This phenomenon, called redshift, is the universe's way of showing its hand. Just as a siren's pitch drops as an ambulance speeds away, stretching the sound waves, light from receding galaxies gets stretched too, shifted toward the red end of the spectrum. But while sound waves compress or expand in air, light stretches because space itself is expanding between us and the source. Imagine two galaxies drifting apart like dots on that inflating balloon. As space stretches, the light traveling between them gets pulled like taffy, its wavelength elongating. The result, the light appears redder than when it left its home galaxy. The more extreme the redshift, the faster that galaxy appears to be racing away. It's not just a color change, it's a speedometer, revealing velocities that can reach staggering fractions of the speed of light for the most distant objects. The Doppler effect, which makes a passing ambulance's siren drop in pitch, is a close cousin to redshift, but there's a key difference. Sound needs air to travel, while light moves through the vacuum of space, stretching because the universe itself is growing. Picture two runners on a treadmill. With sound, it's like one runner speeding up while the treadmill stays still. With light, it's as if the treadmill belt is lengthening beneath them, carrying them apart even if they're standing still. Astronomers measure this redshift with spectrographs, breaking starlight into rainbows and hunting for telltale dark lines where elements like hydrogen and helium absorb specific wavelengths. If those lines slide toward the red, the galaxy is fleeing. The greater the slide, the faster the retreat. Some galaxies' light arrives so stretched, it's shifted from visible blue to infrared light our eyes can't even see. This redshift data doesn't just reveal motion, it lets us map the universe's expansion history. By comparing nearby galaxies to faraway ones, we see a pattern. Expansion accelerates over time like a runaway train picking up speed. Those stretched photons are more than ancient light, they're time capsules, carrying stories from an era when space was younger, denser, and expanding at a different rhythm. Every redshift measurement is a whisper from the past, a clue to the universe's greatest mystery, why it's stretching faster than anyone predicted. Scientists expected the universe's expansion to slow down over time. Gravity, after all, pulls everything together: galaxies, stars, even space-time itself. It stood to reason that this cosmic tug-of-war would gradually put the brakes on the Big Bang's initial momentum. But in 1998, two teams of astronomers made a discovery so shocking it turned cosmology upside down. They weren't just measuring expansion, they were watching it speed up. The universe wasn't slowing down, it was accelerating, as if some invisible force had flipped a cosmic switch. Saul Perlmutter's team at the Supernova Cosmology Project had spent years hunting for a specific kind of stellar explosion type 1, a supernova. These cosmic fireworks are perfect mile markers. They all flare with nearly identical brightness, making them ideal for measuring vast distances. By comparing how bright these supernovae appeared in telescopes to how bright they should be, astronomers could calculate exactly how far away they were, and crucially, how fast the universe was stretching when their light began traveling toward us billions of years ago. Then came the anomaly. The most distant supernovae weren't just far away, they were dimmer than anyone predicted. At first, the researchers suspected errors. Maybe dust in space was blocking the light. Perhaps their instruments needed recalibration. But after triple-checking the data, the impossible conclusion remained. These ancient stellar explosions were farther away than any model of a slowing universe could explain. The only possible answer was that expansion had been slower in the past. Space wasn't just growing, it was growing faster now than it had billions of years ago. Picture throwing a ball into the air, expecting it to slow, stop, and fall back down, only to watch it shoot upward faster and faster, defying gravity itself. That's what the universe was doing. The implications were staggering. Something was overpowering gravity on a cosmic scale, pushing galaxies apart with increasing force. That something, scientists realized, must be dark energy, a mysterious repulsive force woven into the fabric of space itself. The discovery earned Perlmutter and his rivals turned, collaborators Brian Schmidt and Adam Rees, the Nobel Prize in 2011. But the celebration came with a humbling truth. We still don't know what dark energy is. It makes up roughly 68% of the universe's energy, yet remains utterly invisible. Its existence forces us to confront the unnerving possibility that space itself harbors a kind of anti-gravity, a pressure that grows stronger as the universe expands. Every second as you watch this video, dark energy stretches the cosmos a little faster, driving galaxies apart toward an increasingly isolated future. And the most unsettling part, we may never fully understand why. Here's the cosmic punchline: gravity, the force that sculpts galaxies and binds planets to their stars, isn't the universe's dominant player. It's not even close. Imagine the cosmos as a vast budget spreadsheet. And when we tally up all the energy and matter in existence, dark energy alone claims a staggering 68%. That's more than twice the combined share of everything else: stars, planets, black holes, even the enigmatic dark matter that haunts the spaces between galaxies. Picture a cosmic pie chart sliced into 3 unequal portions. A tiny sliver, just 5%, represents all the ordinary matter we know and love, the stuff of Earth, the Sun, and every galaxy visible through our telescopes. Another 27% goes to dark matter, the invisible scaffold that holds galaxies together with its gravitational glue, but the lion's share. That belongs to dark energy, a force so dominant, it outweighs all the galaxies in the observable universe by a ratio of 14:1. To grasp how lopsided this is, think of a crowded concert hall where every star, planet, and speck of dust in existence represents a single audience member. Now imagine 14 invisible giants towering over them, unseen but dictating the very geometry of the room. That's dark energy's footprint, an overwhelming presence we can't see, touch, or directly measure, yet it controls the fate of everything. And here's what makes it truly bizarre. Unlike gravity, which weakens with distance, dark energy's push grows stronger as the universe expands. It's as if space itself is wired with a kind of anti-gravity, a repulsive force baked into the vacuum. The more the universe stretches, the more dark energy fills the gaps, creating a feedback loop that accelerates expansion indefinitely. This isn't just a theoretical curiosity. Dark energy's dominance explains why the cosmos isn't just growing. It's growing faster with each passing billion years. Left unchecked, this acceleration could one day tear apart galaxies, stars, even atoms in a distant future so extreme, physicists call it the Big Rip. But for now, dark energy remains the universe's silent conductor, orchestrating an expansion that defies everything we once knew about the pull of gravity and the nature of reality itself. Einstein's greatest mistake turned out to be one of his most astonishing near misses. In 1917, while applying his theory of general relativity to the entire universe, he faced a problem. His equations insisted the cosmos should either expand or collapse. But like most scientists of his era, Einstein believed the universe was static, eternal, and unchanging. So he tweaked his calculations, adding a fudge factor he called the cosmological constant, a kind of mathematical placeholder representing a repulsive force that would precisely balance gravity's pull, keeping the universe frozen in perfect equilibrium. Then came Edwin Hubble's bombshell discovery in 1929. The universe wasn't static at all. Galaxies were racing apart, space itself stretching. Einstein, realizing his cosmological constant was unnecessary, famously dismissed it as his biggest blunder. He crossed it out of his equations, calling it superfluous. But the story doesn't end there. Nearly 70 years later, when astronomers discovered the universe's expansion was accelerating, they faced the same dilemma Einstein had, except this time, the numbers demanded an anti-gravity force to explain what they were seeing. The cosmological constant wasn't a blunder after all. It was a prophecy. Modern cosmology resurrected Einstein's discarded idea, rebranding it as dark energy. The equations matched almost perfectly. That tiny repulsive term he'd scribbled out now described the very force pushing galaxies apart at ever-increasing speeds. Imagine Einstein's ghost watching from the shadows as scientists dusted off his old notebooks, realizing he'd unknowingly predicted dark energy decades before anyone could prove it existed. It's as if Shakespeare had tossed out a random line in a draft, only for it to become the key to a scientific revolution centuries later. But here's the twist: while the cosmological constant fits the data, it's not the only explanation for dark energy. Some theorists argue it might represent a dynamic field permeating space, like an invisible cosmic fuel that drives expansion. Others propose Einstein's general relativity itself might need revising at cosmic scales. The debate rages on, with Nobel laureates and upstart physicists clashing over whether the cosmological constant's revival is a triumph or a stopgap on the road to a deeper theory. What's clear is this: Einstein's blunder underscores how even geniuses can misread their own breakthroughs. He had the right equation but the wrong intuition, blinded by the dogma of his time. Today, as telescopes peer deeper into the accelerating universe, his cosmological constant stands as a humbling reminder. The cosmos often reserves its boldest truths for those willing to question not just their answers but their assumptions. The universe leaves clues everywhere if you know where to look. Among the most reliable signals are Type 1, a supernova, stellar explosions so uniform in brightness they serve as cosmic lighthouses. Picture a dynamite factory where every stick detonates with identical force no matter when or where it blows up. That's the consistency of these supernovae, triggered when white dwarf stars siphon too much mass from a companion until they reach a critical threshold and erupt in a cataclysm visible across billions of light years. What makes them so valuable is their predictability. Unlike other supernovae, which vary wildly in energy output, Type 1 explosions always peak at the same intrinsic brightness. It's physics at its most obedient. The white dwarf's mass hits exactly 1.4 times that of our Sun before detonating, creating a near-identical blast every single time. Astronomers call them standard candles, celestial yardsticks whose true brightness we know, allowing us to calculate their distance by how dim they appear from Earth. Here's how it works. Imagine holding two identical light bulbs, one in your hand, the other placed a mile away. The distant bulb looks fainter, and the degree of dimming reveals exactly how far it is. Type 1, a supernova, work the same way, except their light travels millions or even billions of years before reaching us. By comparing their known brightness to how dim they appear in telescopes, scientists can pinpoint their distance with remarkable precision. But these explosions aren't just distance markers, they're time machines. The light from the most distant Type 1, a supernova, left when the universe was half its current age. By measuring how much the expansion of space has stretched their light, that redshift we discussed earlier, astronomers can reconstruct how fast the universe was growing at different epochs. It's like finding fossilized ripples from a stone dropped in a pond billions of years ago, then using their size and spacing to calculate how much the pond has expanded since. The catch: these supernovae are rare, appearing in a given galaxy only once or twice per millennium. To find enough of them, researchers must scan thousands of galaxies nightly, hunting for that telltale flare, a single new point of light where none existed before. Modern sky surveys use robotic telescopes and AI to flag potential candidates within minutes of detection, racing to observe them at peak brightness before they fade. It's a cosmic stakeout, with scientists waiting months or years for that one pivotal explosion that could refine our understanding of universal expansion. And refine it they have. Without Type 1, a supernova, we might never have discovered dark energy's role in accelerating the universe. Their unwavering brightness exposed the shocking truth. Distant supernova appeared fainter than expansion models predicted, proving space wasn't just growing, it was speeding up. Every new detection sharpens our measurements, tightening the margins on the Hubble constant and challenging theorists to explain why different measurement techniques still disagree. These stellar explosions are more than just cosmic yardsticks, they're the flashing emergency lights alerting us to the universe's greatest unsolved mysteries. Long before galaxies or stars existed, the universe was a seething ocean of plasma, a superheated soup of particles so dense, light couldn't travel more than a fraction of an inch before bouncing off another particle. But within that chaos, sound waves rippled through the cosmos like vibrations through a struck bell. These weren't ordinary sound waves, they were pressure fluctuations moving at half the speed of light, compressing and rareifying the plasma in a rhythmic dance. And today, billions of years later, the frozen echoes of those waves still linger in the cosmos, etched into the distribution of galaxies like cosmic fingerprints. Scientists call them Baryon acoustic oscillations, and they're one of the most precise tools we have for measuring universal expansion. Imagine dropping a pebble into a still pond. Ripple patterns expand outward, creating rings where water is pushed together or pulled apart. Now picture that same process happening in the early universe's plasma, but instead of water molecules, it's protons, electrons, and photons colliding in a scorching frenzy. Gravity pulled matter toward the denser regions of these pressure waves, while radiation pressure pushed it away. The result, a tug of war that lasted until the universe cooled enough for atoms to form, freezing the waves in place like a snapshot of that primordial chaos. What's astonishing is how these oscillations became a cosmic measuring tape. The sound waves traveled a fixed distance about 500,000 light-years before the universe cooled and froze their pattern. That distance became a standard ruler imprinted across the cosmos. Today, when astronomers map millions of galaxies, they find a curious pattern. Galaxies are slightly more likely to be separated by this exact scale than any other distance. It's as if the universe has a hidden grid with preferred spacings that trace back to those ancient sound waves. Measuring these baryon acoustic oscillations is like finding fossilized ripples in the fabric of space itself. By comparing the expected size of these frozen waves to how stretched they appear in telescope surveys, scientists can calculate how much the universe has expanded since the patterns formed. It's a cosmic version of holding a ruler up to the sky and watching the markings shift over time. And here's where it gets even wilder. These oscillations don't just confirm universal expansion. They also help pinpoint the influence of dark energy. Just as supernova revealed acceleration, baryon acoustic oscillations refine the timeline, showing how expansion changed from the universe's youth to today. The data paints a consistent picture. Dark energy's push has been dominating gravity's pull for billions of years, stretching those primordial sound waves farther apart than anyone expected. The next time you look up at the night sky, remember this: the galaxies above aren't randomly scattered. Their positions carry the echo of a time when the universe was a screaming, roiling storm of plasma, ringing with sound waves that would one day become the yardstick by which we measure the fate of everything. Here's a cosmic mystery that's keeping astrophysicists awake at night, a discrepancy so stubborn, it's called the Hubble tension. On one side, we have meticulous measurements of the early universe from the cosmic microwave background, that afterglow from the Big Bang. On the other, cutting-edge observations of modern galaxies and supernova. Both methods are incredibly precise, both follow rigorous physics, yet they stubbornly disagree on how fast the universe is expanding right now, differing by about 9%. It's as if two world-class chefs followed the same recipe but pulled cakes from the oven that were undeniably different sizes. Let's break down the teams in this cosmic standoff. Team Early Universe uses the Planck satellite's ultra-detailed maps of the cosmic microwave background. These ancient light patterns, frozen when the universe was just 380,000 years old, let scientists calculate what the Hubble constant should be today based on our best models of cosmic evolution. Their answer, 67.4 kilometers per second per megaparsec, a value so precise, it's like measuring the width of a hair from 2 miles away. Then there's Team Modern Universe, led by astronomers observing pulsating stars called Cepheids and Type 1, a supernova in nearby galaxies. By carefully tracking these cosmic yardsticks, they've nailed down today's expansion rate at 73 kilometers per second per megaparsec. That extra 5.6 might sound trivial, but in cosmology, it's a chasm. At cosmic distances, this gap means galaxies billions of years from now could be radically farther apart than our models predict. The plot thickens because both methods have been refined to razor-sharp precision. The cosmic microwave background measurements have cross-checked with gravitational lensing and baryon acoustic oscillations. The modern measurements have been verified by independent teams using different telescopes and techniques. Yet the discrepancy won't budge. It's not experimental error. It's as if the universe changed its expansion rate when we weren't looking. This tension has sparked a gold rush of theories. Maybe dark energy isn't constant but evolves over time, subtly tweaking expansion. Perhaps there's an undiscovered particle, a dark radiation, that briefly flooded the early universe. Some daring physicists even suggest gravity itself works differently on cosmic scales, requiring modifications to Einstein's relativity. Each idea has consequences. If dark energy changes, it could mean the universe's fate is stranger than we thought. If gravity needs updating, it would rewrite fundamental physics, the most unsettling possibility, that we're seeing cracks in our standard model of cosmology, the beautifully successful framework that's explained so much about the universe. Like Newtonian physics before quantum mechanics, it may be incomplete, waiting for its Einstein to reveal a deeper layer of cosmic truth. For now, telescopes worldwide are racing to settle the debate, measuring the Hubble constant with methods ranging from gravitational waves to quasars. Every new measurement tightens the screws, forcing theorists to either reconcile the numbers or embrace revolutionary ideas. What makes this so electrifying isn't just the scientific discord, it's what the resolution could reveal. Historically, when physics hits a stubborn discrepancy, it's often the prelude to a breakthrough. The orbit of Mercury's perihelion hinted at general relativity. The ultraviolet catastrophe birthed quantum theory. The Hubble tension might be our generation's clue that the cosmos holds secrets far stranger than we've dared imagine. Until then, it remains the universe's most tantalizing unsolved math problem, one where the answer could rewrite everything we know about space, time, and existence itself. Imagine holding a photograph of yourself as a newborn, faded, grainy, but unmistakably you. Now picture the universe with its own baby picture, taken when it was just 380,000 years old. This is the cosmic microwave background, or CMB, the oldest light in existence, a snapshot of the universe's fiery infancy. Captured in stunning detail by the Planck satellite, this radiation map isn't just a relic. It's a treasure trove of secrets about how fast space was stretching in those early moments, setting the stage for everything that followed. What makes the CMB so special is its imperfections. If the early universe had been perfectly smooth, we wouldn't exist. Instead, the Planck map reveals a speckled pattern of slightly hotter and cooler spots, temperature variations as tiny as 1 part in 100,000. These aren't random flaws, they're cosmic fossils, imprints of quantum fluctuations that emerged trillionths of a second after the Big Bang, stretched to astronomical scales by inflation. Like raindrops frozen in mud, they preserve the shape of the universe's very first moments. Here's how it works. When the Planck satellite scanned the sky, it measured these temperature differences with precision finer than a millionth of a degree. The hotter regions, those were denser patches where gravity's pull was slightly stronger. The cooler spots, sparse areas where matter was thinner. But the real magic lies in the spacing between these fluctuations. Just like Baryan acoustic oscillations, they're spaced at regular intervals, echoes of those primordial sound waves traveling through the early plasma. By analyzing these patterns, scientists can calculate how rapidly the universe was expanding when the CMB light broke free. It's like measuring the stretch marks on a balloon to figure out how fast it was inflated. Planck's data pinned the early expansion rate, the Hubble constant, to 67.4 kilometers per second per megaparsec, a number so precise, it's equivalent to weighing the Earth to within a single grain of sand. But the CMB doesn't just give us a speed limit from the past. Those temperature fluctuations also encode the universe's ingredients, the exact mix of ordinary matter, and dark energy needed to create the cosmos we see today. It's a cosmic recipe written in degrees Kelvin, and it's why the Planck measurements are so foundational. They anchor our entire timeline of cosmic history from the first picosecond to the present. Yet this baby picture also deepens the Hubble tension mystery. The expansion rate it predicts for today's universe is stubbornly lower than what we observe from galaxies and supernova. Either there's a hidden ingredient tweaking the numbers, or our understanding of cosmic adolescence has gaps we've yet to fathom. The CMB isn't just a relic, it's a puzzle, a mirror held up to our theories, showing us how much we still don't know about the universe's growth spurt. And here's the wildest part, that faint glow bathing the cosmos, it's all around you. Hold up an old analog television between stations, about 1% of the static is CMB photons, particles that have traveled for 13.8 billion years to reach your living room. They're the universe's first light, whispering across time, carrying secrets from an era when space itself was just learning how to stretch. Quasars are the universe's lighthouses, beacons so brilliant they outshine entire galaxies. Packed into a space smaller than our solar system, these ultra-bright cores of distant galaxies blast out enough light to be seen clear across the observable universe. At their hearts, supermassive black holes gulp down staggering amounts of gas and dust, heating it to millions of degrees until it glows with the brightness of a trillion suns. But beyond their spectacle, quasars hold a secret. They're cosmic mileposts, helping astronomers measure how fast space was stretching billions of years ago. To grasp their scale, picture this. A single quasar can outshine every star in its host galaxy combined. Imagine a tiny flashlight bulb glowing brighter than the combined output of every spotlight in a major city. That's the luminosity imbalance we're dealing with. This extreme brightness makes quasars visible across mind-boggling distances, even when their host galaxies fade into obscurity. The most distant quasar we've found, Joan 327+18, beams light from an era when the universe was just 670 million years old, a mere 5% of its current age. But how do we use these cosmic blowtorches to measure expansion? The trick lies in their variability. Quasars don't shine steadily, they flicker, brightening and dimming over months or years as their black holes guzzle matter in erratic bursts. By tracking these fluctuations and comparing them to the quasar's redshift, scientists can estimate its distance independently of other methods. It's like watching a distant lighthouse whose bulb cycles between high and low brightness. The timing of those cycles, combined with how stretched its light appears, reveals how far away it is and how much space has expanded since its photons began their journey. The real power comes when we stack quasars against other distance markers. Type 1, a supernova, give precise measurements for recent cosmic history, the last few billion years. Quasars extend our reach deeper, probing epochs when the universe was far younger and expansion behaved differently. Together, they form complementary chapters in the universe's growth chart. Recent surveys like the Sloan Digital Sky Survey have mapped hundreds of thousands of quasars, creating a three-dimensional cosmic web that reveals how expansion rates changed across different eras. Yet quasars come with quirks. Unlike supernova, which are near-identical explosive events, quasars vary widely in their intrinsic brightness. Astronomers must cleverly account for this by studying statistical patterns in large samples or identifying telltale signatures in their light spectra. It's forensic cosmology, piecing together clues from the universe's most energetic objects to reconstruct its expansion history. When combined with baryon acoustic oscillations and CMB data, quasars help triangulate the Hubble constant from multiple angles, adding weight to the growing tension between early and modern universe measurements. What's truly humbling is realizing these dazzling objects are time capsules. The light from ancient quasars shows us space when it was more compact, before dark energy's push became dominant. Some quasars we observe today may no longer exist. Their light has traveled so long. Their black holes might have starved or collided in the intervening billions of years. Yet their photons still arrive, carrying encoded messages about how space-time stretched during the universe's fiery youth. Every flicker, every spectral line shifted toward the red, is part of a grand cosmic crossword puzzle, one where the clues span billions of light years and the prize is understanding the fate of everything. Einstein's theory of general relativity made a wild prediction. Massive objects don't just pull on things with gravity, they actually bend the fabric of space itself, warping the path of light like a bowling ball distorting a trampoline. This phenomenon, called gravitational lensing, isn't just a cosmic curiosity, it's become one of our sharpest tools for measuring the universe's expansion. When light from distant galaxies passes near massive galaxy clusters, it doesn't travel in a straight line. Instead, it curves around these cosmic heavyweights, creating distorted, magnified, or even duplicated images of background objects. One of the most famous examples is Hubble's smiley face image, a galaxy cluster so massive, it bent light from galaxies far behind it into perfect arcs that resembled a grinning cosmic Cheshire cat. But beyond their visual spectacle, these lensed images hold precise mathematical clues. By measuring how severely the light is distorted, astronomers can calculate the total mass of the foreground cluster, including its invisible dark matter halo. Even more crucially, the degree of bending reveals the relative distances between Earth, the lensing cluster, and the background galaxy. Here's where expansion comes into play. Since the amount of light bending depends on how far each object is from the others, and because the universe's expansion stretches those distances over time, gravitational lensing effectively gives us a way to triangulate the Hubble constant. Imagine trying to measure the distance to a mountain by looking at how its reflection warps in a lake. The more you know about the lake's curvature and the mountain's position, the better you can calculate the scale of the landscape. Lensing works similarly, with galaxy clusters serving as the universe's natural magnifying glasses. The most powerful lenses don't just create arcs, they produce multiple images of the same background object, each taking slightly different paths around the cluster. Because space is expanding while the light travels, these duplicated images often arrive at Earth at slightly different times, with delays that can range from days to years. By comparing these time delays, essentially cosmic stopwatch measurements, scientists can work backward to determine how much the universe stretched during the light's journey. It's like watching two race cars take different routes to the same finish line. The difference in their arrival times tells you how much the track itself expanded during the race. Recent surveys like the Dark Energy Survey and the upcoming Vera Rubin Observatory are mapping thousands of these gravitational lenses, creating a statistical web of cosmic distances that independently cross-checks other expansion measurements. Some analyses even use subtle distortions in the shapes of millions of distant galaxies, weak lensing, to trace the universe's large-scale structure and how it's being stretched by dark energy. The results consistently point to an accelerating expansion, though with enough precision to keep fueling the Hubble tension debate. What's remarkable is how these warped images, once dismissed as optical illusions, have become precision instruments. Every stretched arc, every duplicated quasar, is a testament to spacetime's flexibility and a measuring stick for its relentless expansion. The universe literally bends light to show us its secrets, revealing not just where we are in space, but how fast the stage itself is growing beneath our feet. There's a cosmic clock discrepancy that's baffling scientists, a rift in time itself. On one hand, we have the universe's birth certificate, the cosmic microwave background, that ancient light from 380,000 years after the Big Bang, which confidently declares our cosmos is 13.8 billion years old. But recent measurements of the universe's accelerating expansion suggest something startling. If space has been stretching faster than we thought, the math implies a younger universe, perhaps only 12.5 billion years old. That's a gap of 1.3 billion years, enough time for galaxies to form, stars to die, and planets to cool. Picture two identical hourglasses, one filled with sand, the other with water. Both measure time, but because water flows faster, the second hourglass empties sooner. The universe has similar competing clocks. The CMB method assumes a steady, predictable expansion rate based on early universe physics, like counting sand grains in that first hourglass. But modern measurements act like the water clock, revealing expansion has sped up under dark energy's influence, shortening the apparent age. Here's where it gets thorny. If we calculate backward from today's accelerated expansion, galaxies wouldn't have needed as much time to reach their current distances, hence the younger age estimate. But this clashes with independent evidence like the ages of ancient stars and radioactive decay in meteorites, which align with the older CMB timeline. It's like finding a tree with rings indicating it's 1,000 years old, while carbon dating insists it's only 700. The tension arises because dark energy's acceleration doesn't just affect the present, it rewinds the cosmic movie differently. Think of a car trip where you alternate between cruising and slamming the gas pedal. If you only knew the final distance and average speed, you'd miscalculate the trip's duration unless you accounted for those bursts of acceleration. Similarly, if dark energy's push varied over cosmic history, our age calculations could be drastically off. Some theorists propose radical solutions. Perhaps dark energy was stronger in the past, or the early universe cooled faster than expected, skewing our CMB interpretations. Others suggest exotic particles altered the expansion rate during cosmic adolescence. But each fix comes with trade-offs, forcing scientists to weigh which evidence is more reliable: the pristine snapshot of the infant universe or the dynamic behavior of galaxies we see today. What's undeniable is this paradox exposes gaps in our cosmic chronology. Whether the universe is 13.8 or 12.5 billion years old isn't just academic. It reshapes our understanding of how quickly galaxies assembled, how early stars ignited, and whether the cosmos had a dark age, lasting hundreds of millions of years or barely a cosmic blink. Every conflicting measurement is a crack in the foundation of modern cosmology, hinting that the universe's timeline might need more than a slight adjustment. It might demand a rewrite. Picture the universe as a cosmic tug-of-war, where dark energy isn't just winning, it's growing stronger with every passing second. Now consider this nightmare scenario. What if that acceleration doesn't just continue but spirals out of control? Scientists call this theoretical endpoint the Big Rip, a doomsday where dark energy morphs into something far more sinister: phantom energy. Unlike ordinary dark energy, which maintains a steady push, phantom energy gains strength as the universe expands, like a car with an accelerator pedal stuck to the floor. The consequences: a timeline so violent it rewrites the laws of physics on its way to oblivion. The first signs would be subtle. Billions of years from now, galaxies beyond our local group would redshift into invisibility as space stretches faster than light can traverse it. The cosmic horizon would shrink, leaving future astronomers with a sky devoid of external galaxies, a lonely island in an ever-darkening void. But the real horror begins when phantom energy's grip tightens. Around 60 million years before doomsday, gravitational bonds between galaxies would snap. The Milky Way and Andromeda, destined to merge in a far gentler timeline, would instead be wrenched apart as the space between them expands too rapidly for gravity to hold them together. Then comes the stellar carnage. 20,000 years before the end, phantom energy's exponential growth would overcome the gravity holding individual stars together. Solar systems would disintegrate, planets torn from their suns like marbles scattered across an inflating rubber sheet. 3 months prior, stars themselves would unravel as their internal gravity loses the battle against the stretching of space-time. The final minutes would be apocalyptic. Planetary orbits disintegrate, Earth's crust fractures, and the very molecules in our bodies strain against forces they were never designed to withstand. The last microseconds would be pure physics horror. Atomic nuclei, bound by the strongest force in nature, would be shredded as space itself expands faster than the speed of light at subatomic scales. Protons and neutrons would dissolve into quark soup. Then those quarks would be carried beyond causal contact with each other, every fundamental particle isolated in its own infinitesimal pocket of oblivion. Time, space, and matter would cease to have meaning in a reality where no two particles can ever interact again. What makes phantom energy so chilling isn't just the violence of the end, but the inevitability. Unlike black hole collisions or asteroid impacts, this isn't an external threat. It's woven into the fabric of space itself, a runaway process with no off switch. And while current data suggests dark energy behaves more gently, phantom energy remains a plausible, if extreme, outcome should its properties ever shift. It's the universe's ultimate failsafe, a reminder that even the vacuum of space might one day turn against everything it once nurtured. The Hubble constants units sound like something ripped from a theoretical physics nightmare: 70 kilometers per second per megaparsec. But peel back the jargon, and this bizarre measurement reveals a simple, mind-bending truth about how space stretches. Think of it like a cosmic speed limit sign, but instead of cars on a highway, it's galaxies racing apart, and the farther they are, the faster they go. Let's break it down. A megaparsec is about 3.26 million light-years, an almost unimaginable distance. Now imagine two galaxies sitting exactly 1 megaparsec apart. The Hubble constant tells us that, on average, the expansion of space between them adds 70 kilometers per second to their separation velocity. That's like two cars on an endless freeway where for every mile they drift apart, the speedometer ticks up by 43 miles per hour. But here's the twist: it's not the galaxies moving, it's the road itself stretching beneath them. To grasp just how strange this is, picture a rubber band with marks every inch. Stretch it gently and nearby marks barely move apart. But the farther two marks are, the faster the gap between them grows, not because the marks are sliding, but because the rubber itself is elongating. Now scale that up to galactic proportions. A galaxy 10 megaparsecs away, space's expansion carries it away at 700 kilometers per second, 100 megaparsecs. 7,000 kilometers per second. At these distances, space's stretch outpaces even the speed of light for galaxies beyond our cosmic horizon, rendering them forever invisible. What's wild is how this single number, 70 kilometers per second per megaparsec, anchors our entire cosmic timeline. Flip it upside down and you get the Hubble time, roughly 14 billion years, an estimate for the universe's age if expansion had been constant since the Big Bang. Of course, we know dark energy complicated that story, but the fact that this quirky unit connects directly to the cosmos lifespan is a beautiful example of how deeply intertwined our measurements are with reality's fabric. And yet, for all its precision, the Hubble constant remains at the heart of astronomy's biggest feud. Is it 67, as the cosmic microwave background suggests, or 73 per supernova measurements? That gap might seem small, but in a universe where distances compound exponentially, it's the difference between a cosmos that's 13.8 billion years old and one that's noticeably younger. Every decimal point in those kilometers per second per megaparsec carries weight, reshaping our understanding of dark energy, cosmic fate, and whether Einstein's blunder was really a blunder at all. So next time you hear 70 kilometers per second per megaparsec, don't let the jargon glaze your eyes. It's not just a unit, it's the universe's heartbeat, a numerical pulse tracking how fast everything we know is growing colder, lonelier, and more mysterious with each passing second. Measuring cosmic expansion should be straightforward. Pick reference points, track distances, and calculate the rate. Yet astronomers face a puzzle that depends entirely on where they look. Nearby Cepheid variable stars, our cosmic yardsticks within the Milky Way and neighboring galaxies, tell one story. Distant quasars blazing from the edge of the observable universe whisper another. The contradiction between these local and global measurements isn't just academic, it's a rift threatening to crack open our understanding of spacetime itself. Start with Cepheids, the universe's pulsating lighthouses. These yellow supergiant stars rhythmically brighten and dim over days or weeks. With a twist, their pulse rate directly correlates to their true brightness. Discover this pattern and you've got a standard candle. Measure how dim a Cepheid appears from Earth, compare it to its known luminosity, and voila, you've calculated its distance. Hubble himself used them to prove galaxies existed beyond the Milky Way. Today, space telescopes like Hubble and JWST study Cepheids in our cosmic backyard with staggering precision, nailing down expansion rates within a few 100 million light-years. Their verdict, 73 kilometers per second per megaparsec. Now shift your gaze 13 billion light-years away to quasars. These ancient beacons allow astronomers to measure expansion during the universe's rowdy adolescence, when dark energy's influence was just awakening. But here's the rub. When you chain these measurements together, Cepheids setting the local scale, supernova bridging the mid-range, and quasars marking the deep frontier, the numbers diverge. Early universe methods like the cosmic microwave background suggest a gentler expansion, 67. That 6-unit gap might seem trivial, but over cosmic distances, it's the difference between a universe that's 13.8 billion years old and one that's noticeably younger. The discrepancy could arise from measurement errors, except both methods have been cross-checked relentlessly. Cepheid distances are calibrated using parallax, watching how their positions shift as Earth orbits the Sun, a technique accurate to within 1%. Quasar measurements leverage gravitational lensing and spectral fingerprints, verified by independent teams. The more likely explanation: the universe's expansion isn't uniform. Perhaps dark energy's strength has changed over time, or unknown physics tweaks gravity at vast scales. Imagine measuring a rubber band stretch at one end and getting different results than the other. It implies hidden forces warping the material itself. This local versus global tension forces astronomers to play cosmic detective. Some suspect early dark energy, briefly turbocharged expansion after the Big Bang. Others propose our local group of galaxies inhabits a peculiar void, skewing nearby measurements. The most radical solution: gravity might behave differently across cosmic epochs, requiring revisions to Einstein's equations. Each theory carries high stakes, not just for the Hubble constant, but for predicting whether the universe will end in a big rip or a slow fade. What makes this debate electrifying is how it mirrors the scientific process itself. When two impeccable methods disagree, either someone missed a subtle error or nature is hinting at deeper laws. As next-generation telescopes like the Roman Space Telescope join the hunt, they'll scrutinize both Cepheids and quasars with unprecedented sharpness. Will the gap narrow or yawn wider? Either outcome promises revelations. After all, the universe rarely contradicts itself without reason. When it does, it's usually about to teach us something extraordinary. Empty space isn't empty, not by a long shot. If you could peer into the quantum realm, you'd see a seething, frothing chaos where particles blink into existence and vanish in fractions of a second. These quantum vacuum fluctuations are nature's ultimate sleight of hand, with virtual particle pairs matter and antimatter constantly erupting from nothingness before annihilating each other almost instantly. It's as if the universe is a bubbling pot of water, with bubbles forming and popping too quickly to see. But here's the mind-blowing part: this quantum foam might hold the key to dark energy itself. Imagine space as a vast, invisible ocean. On the surface, it seems calm and still, but dive deeper and you'll find turbulent currents swirling beneath. Every cubic centimeter of empty space bursts with these fleeting particle pairs, borrowing energy from the universe just long enough to exist before paying it back. Normally, they cancel each other out perfectly. But what if they don't? Some theories suggest dark energy could be the leftover pressure from these quantum fluctuations, a tiny, persistent push that adds up across the cosmos, stretching spacetime itself like an invisible spring. The math behind this is both elegant and maddening. When physicists calculate how much energy these virtual particles should contribute to the vacuum of space, the number is absurdly large, enough to rip atoms apart instantly. Yet we don't see that chaos. Instead, dark energy's measured effect is staggeringly small, like finding a single grain of sand in a desert the size of the observable universe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Why does reality ignore 99.99% of the vacuum's calculated energy? One radical idea is that we're missing a hidden symmetry or cancellation mechanism in quantum field theory, some elegant twist that makes most of this energy vanish. Others propose dark energy isn't constant but ebbs and flows, tied to the ever-shifting quantum froth. There's even a wild hypothesis that our universe is just one bubble in an infinite multiverse, where different regions have wildly different vacuum energies, and we happen to live in a pocket where the numbers align just right for galaxies and life to exist. What's undeniable is how deeply these quantum ripples connect to the cosmos' fate. Every second, as virtual particles flicker in and out of being, they might be weaving the fabric of expansion itself. The same quantum rules that govern atoms could be steering the universe toward a cold, dark future, or something even stranger. It's a reminder that nothing, not even empty space, is ever truly at rest. Here's something that might unsettle your cosmic perspective. Our entire galaxy, along with our neighboring galactic companions, might be sitting inside a colossal cosmic void. Not just any void, but one so massive it could be throwing off our measurements of universal expansion. Astronomers call it the KBC void, named after the researchers Keenan, Barger, and Cowie, who first identified its staggering scale. An underdense region spanning roughly 2 billion light-years, making it the largest known structure of its kind in the observable universe. Picture a bubble so vast, thousands of galaxies could fit inside with room to spare. Now imagine we're floating near its center, like a single speck of dust suspended in the middle of an empty sports stadium. That's essentially our position within the KBC void. Most of the universe isn't like this. Out there, galaxies cluster into dense filaments and walls, forming a vast cosmic web. But here, it's eerily sparse, a galactic desert where matter is spread thin compared to the bustling neighborhoods beyond. Why does this matter? Because voids aren't just empty space, they warp our perception of cosmic expansion. Gravity behaves differently here. With less matter pulling inward, the space inside a void expands slightly faster than the denser regions outside. Think of it like a balloon with patches of thick and thin rubber. The thinner sections stretch more easily under pressure. If we're inside such a region, our local measurements of the Hubble constant might be slightly inflated, like a speedometer calibrated on a downhill slope. This could help explain the Hubble tension. If the KBC void's underdensity is skewing our nearby measurements, it might account for why local galaxies appear to be racing away faster than the early universe's expansion rate suggests. Some calculations show the void's effect could bridge up to half the gap between the conflicting values. It's like realizing your bathroom scale was on a slight tilt suddenly. The numbers make more sense. But the KBC void isn't just a convenient fix. Its existence challenges our assumptions about the universe's uniformity. The cosmic microwave background suggests matter should be evenly distributed on large scales, yet here we are in a bizarrely empty pocket. Is this a statistical fluke or evidence of a cosmos far lumpier than we thought? Future galaxy surveys, like those from the Vera Rubin Observatory, will map the void's edges in unprecedented detail, testing whether it's truly as vast and empty as it seems. For now, the KBC void remains a humbling reminder. Our cosmic address might be more unusual than we realized. Every measurement we take, every calculation we make, is filtered through the lens of this immense nothingness. It's a cosmic hall of mirrors, distorting our view just enough to keep us guessing. And that's the beauty of it. The universe isn't just expanding, it's full of surprises, even in the emptiest corners. Neutrinos are the universe's ultimate ghosts, particles so ethereal. They pass through planets like moonlight through glass. Every second, trillions of these subatomic wisps stream through your body, unaffected by walls, mountains, or even entire stars. Yet despite their uncanny ability to ignore matter, these ghostly particles exert a tiny but measurable drag on cosmic expansion, like an invisible hand gently pressing against the accelerator of the universe. If you held a Geiger counter tuned to neutrinos, your whole body would click non-stop, not from radioactivity, but from the faint afterglow of particles that have traveled billions of light years to reach you. Here's the twist: neutrinos are almost massless, but almost is the key word. Each neutrino carries a whisper of weight, about 1/10,000,000th the mass of an electron. That seems negligible until you account for their staggering numbers. The Big Bang flooded the cosmos with primordial neutrinos, and they've been drifting through space ever since, outnumbering atoms in the universe by 1 billion to 1. All that collective mass spread across such vast numbers creates a subtle gravitational pull. Unlike dark energy's repulsive push, neutrinos tug ever so slightly in the opposite direction, acting as cosmic speed bumps against expansion. To grasp their impact, picture a vast ocean where dark energy is the wind, stretching the surface into ever larger waves. Now imagine trillions of tiny plankton suspended in that water, each one barely noticeable, but together creating enough drag to slow the wave's growth. That's the neutrino effect. Current models suggest their gravitational influence may have trimmed the universe's expansion rate by about 1% over 13.8 billion years. It's a minuscule adjustment, but in cosmology, even a 1% tweak can reshape entire timelines. What's wild is how we detect these cosmic phantoms. Massive underground tanks filled with ultra-pure water or liquid argon wait silently for the rare neutrino that actually interacts with matter. When one does, it emits a flash of light or charged particle, triggering sensors that scream, "Here I am." Most neutrinos, of course, pass through undetected, a reminder of how much we're missing in the shadows. Yet even as ghosts, they leave fingerprints on the cosmos. The way galaxies cluster, the faint temperature variations in the cosmic microwave background, all bear subtle imprints of neutrinos' gravitational whispers. Future observatories like the Deep Underground Neutrino Experiment aim to catch them in unprecedented numbers, potentially revealing whether their masses or abundances could resolve parts of the Hubble tension. So while dark energy dominates the cosmic tug-of-war, neutrinos are the quiet counterbalance, reminding us that even the most elusive particles shape the universe's fate. Every time one passes through you, it carries a secret. The story of expansion isn't just about push and pull, but about trillions of invisible actors, each playing their tiny part in the grand saga of spacetime. One day, far in the future, the night sky will lie to us, the glittering tapestry of galaxies we see today. Each a swirling island of billions of stars will vanish one by one like lights fading on a distant shore. This isn't science fiction, it's the inevitable consequence of the universe's accelerating expansion, a fate written into the fabric of spacetime itself. Imagine the cosmos as a vast ocean where galaxies are ships and dark energy is the tide, relentlessly pulling them apart. Right now, we can still see their lanterns glowing across the dark. But as the tide quickens, those lights will blink out, not because they're dying, but because space itself is stretching faster than their light can reach us. The mechanics are chillingly simple. Every galaxy beyond our local group, a tight cluster of about 60 galaxies gravitationally bound to the Milky Way, is drifting away as space expands between us. Today, we see galaxies billions of light-years distant because their light left when the universe was younger and more compact, but dark energy's grip is tightening. In about 150 billion years, every galaxy outside our local group will have crossed what's called the cosmic light horizon. Their light, struggling against the stretching of space, will never reach us again. The last photons from those distant islands will stretch into oblivion, their wavelength red shifted into undetectable nothingness. Picture a time lapse of this future sky. First, the most distant galaxies wink out, their light stretched beyond infrared into radio waves too faint to detect. Then the middling ones fade like stars swallowed by dawn. Eventually, only our closest galactic neighbors remain, Andromeda, the Triangulum Galaxy, and a handful of dwarfs, all locked in a slow-motion dance with the Milky Way. Beyond them, pure black, the cosmic microwave background, that faint glow from the Big Bang, will have redshifted into complete invisibility. Future astronomers, if any still exist, will peer into telescopes and see only emptiness. No evidence of other galaxies, no hint that the universe was once crowded with light, just an eternal void. This isolation reshapes everything we know about cosmology. Civilizations born in that distant era will have no way to deduce the Big Bang or an expanding universe. their night sky will show only a static island universe, a single galaxy adrift in darkness. All clues to dark energy, to the cosmic web, to the universe's fiery beginnings, will have receded beyond the reach of observation. It's as if the cosmos is erasing its own history, leaving future beings to wonder if they're alone in a finite, unchanging void. The cruel irony, those galaxies aren't gone. They're still out there, their stars burning for trillions of years, but space between us is stretching faster than light can traverse it, cutting us off from their existence as surely as if they'd vanished. The universe isn't dying, it's disconnecting, isolating pockets of matter in ever-shrinking islands of causality. And this isn't some abstract billion-year-later problem. Right now, at this very second, galaxies are crossing that horizon, disappearing from our future's view. With every passing moment, the observable universe shrinks, like a room where the walls keep receding, but the doors are closing faster. What's left will be a cosmic graveyard, a Milky Way merged with Andromeda, its stars burning low and red, orbiting a supermassive black hole that slowly consumes what remains. No new stars will form. All gas and dust will have been used up or flung away by dying stars. The last civilizations, if they endure, will huddle around black holes, mining their Hawking radiation for energy in a cold, dark universe. And beyond their bubble of warmth, nothing but an endless, featureless expanse where once there were galaxies. The universe won't end with a bang or even a whimper, but with a silence so complete not even light can break it. The universe plays a strange trick with time. Its most dramatic transformations happen in the blink of a cosmic eye, while its slowest burns unfold over epochs. Take inflation, that explosive burst of growth in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. Space didn't just expand then, it hyperventilated, doubling in size at least 90 times faster than you can snap your fingers. Picture blowing up a balloon to the size of Earth, then suddenly inflating it to the width of the observable universe before your next heartbeat. That's inflation's raw, unfiltered power. Now fast forward 13.8 billion years. Dark energy's acceleration seems glacial by comparison. Space still grows, but at a rate that would make a snail impatient just a few percent every billion years. Yet these seemingly opposite bookends of cosmic history share a haunting similarity. Both defy gravity's pull. Inflation overcame the crushing density of the primordial universe, while dark energy now overpowers the collective gravity of galaxies and dark matter. The difference, one was a sprint, the other is a marathon with no finish line. To grasp the absurd scale difference, imagine compressing the universe's lifespan into a single calendar year. Inflation occupies the first sliver of the first second of January 1st, so brief, it makes a camera flash seem eternal. Dark energy's era, by contrast, begins around December 26th and stretches indefinitely into the future. That's how lopsided these epochs are in duration. But here's the twist, both periods left fingerprints on the cosmos that we can still read today. Inflation's quantum jitters stretched into the cosmic microwave background's temperature variations, the seeds of all galaxies. Dark energy's handiwork shows up in the way supernova redshift as space stretches beneath their light. The mechanisms couldn't be more different, though. Inflation likely came from a scalar field, a kind of cosmic energy syrup that briefly energized empty space before decaying into the particles we know. Dark energy might be the vacuum's intrinsic energy, a gentler pressure that never fades. Some theorists wonder, could dark energy be inflation's feeble echo, a remnant of that primordial fire somehow persisting at ultra-low strength? Or are we seeing two entirely unrelated phenomena, bookending cosmic history with expansion for different reasons? What's certain is this: both epochs remind us how little we understand space's true nature. The same vacuum that birthed galaxies in a violent hiccup now plucks them apart with silent, insistent fingers. The universe's first and last acts might be more connected than we think. or they could be cosmic coincidences, leaving us to wonder if space-time has always carried this latent tendency to stretch, first furiously, then lazily, like an old rubber band losing its snap. Either way, the contrast couldn't be starker, a beginning of unimaginable speed and an end of infinite, creeping stillness. Dark energy may dominate modern cosmology, but not everyone's convinced it's the only answer. A small but vocal faction of physicists argues we're missing something fundamental, that instead of invoking an invisible, repulsive force, we should rethink gravity itself. Enter MND, short for modified Newtonian dynamics, the most famous rebel in this cosmic courtroom drama. Proposed in the 1980s by Israeli physicist Mordechai Milgrom, MND suggests gravity doesn't weaken as sharply over large distances as Newton or Einstein predicted. At galactic scales, it posits a subtle tweak to the rules, one that could explain galaxy rotation curves without invoking dark matter's invisible scaffolding. But MND isn't alone in its heresy. A rogues gallery of alternative theories vies for attention, each with its own tantalizing strengths and stubborn flaws. Take emergent gravity, championed by Dutch physicist Erik Verland. He argues gravity isn't a fundamental force at all, but rather an emergent property of quantum entanglement, a sort of cosmic hologram projecting the illusion of attraction from deeper, information-theoretic processes. Then there's brain world models, which suggest our universe is a four-dimensional membrane floating in higher dimensional space, with gravity leaking in ways that mimic dark energy's effects. Even Einstein's own equations get reconsidered. Some theorists propose adding extra terms or dimensions to general relativity, creating frameworks where cosmic acceleration emerges naturally without dark energy's mysterious push. The appeal of these alternatives lies in their audacity. Why invent a mysterious substance constituting 68% of the universe if tweaking gravity could solve the puzzle? MND supporters point to its uncanny success predicting galaxy rotations without dark matter, a feat mainstream models achieve only by carefully tuning dark matter distributions. But here's the catch: MND struggles spectacularly with larger scales. It can't explain the bullet cluster where colliding galaxies leave visible matter lagging behind their gravitational fingerprints, a phenomenon perfectly explained by dark matter's invisible mass. Nor does it easily account for the cosmic microwave background's intricate patterns, which align exquisitely with standard cosmology's dark energy-dark matter combo. Emergent gravity faces similar hurdles. While elegant in principle, its mathematical machinery remains underdeveloped, unable yet to match the precision of lambda CDM, the reigning standard model of cosmology. Brain world models, meanwhile, drift dangerously close to untestable speculation, invoking higher dimensions that might forever elude detection. And every proposed modification to general relativity must grapple with Einstein's theory's century-long winning streak. It's passed every test from Mercury's orbit to gravitational wave detections with flying colors. Yet these challenges persist, fueled by the nagging sense that dark energy is a placeholder, a mathematical, here be dragons on our cosmic maps. Their very existence enriches cosmology, forcing mainstream researchers to sharpen their arguments and confront uncomfortable gaps. After all, scientific revolutions often begin at the fringes, with ideas initially dismissed as outlandish. Quantum mechanics, plate tectonics, even the Big Bang itself were once rebel theories. The difference this time, we're armed with exponentially more data, allowing us to pit these models against observations in ways Copernicus or Darwin could only dream of. So while lambda CDM remains the heavyweight champion, the underdogs keep swinging. New telescopes like Euclid and the Vera Rubin Observatory will deliver fresh tests, measuring cosmic structures with enough precision to expose which theories crack under pressure. Maybe one of these alternatives will rise to the occasion, or perhaps dark energy will solidify its reign. Either way, the competition ensures we're not just accepting answers, we're demanding the universe prove itself, one gravitational anomaly at a time. For decades, the Hubble Space Telescope was our window into the cosmic deep, capturing images that redefined our place in the universe. Its iconic deep field, a pinprick of sky no larger than a grain of sand held at arm's length, revealed thousands of galaxies crammed into a space once thought empty. But Hubble had limits. Its mirrors couldn't catch the faintest, most ancient light, stretched and dimmed by billions of years of cosmic expansion. Enter the James Webb Space Telescope, or JWST, a technological marvel designed to see what Hubble couldn't: infrared light from the universe's first galaxies, redshifted into oblivion by time itself. Where Hubble's view was like squinting through fog, JWST infrared eyes pierce through cosmic dust and gas with crystalline clarity. Imagine comparing a grainy black and white photo to an ultra-high-definition color panorama. That's the leap in resolution. Take Hubble's famous ultra-deep field, which captured galaxies as they appeared 13 billion years ago. JWST version of the same patch of sky doesn't just add more galaxies, it reveals their structures in shocking detail. Spiral arms, star-forming regions, even the faint glow of primordial hydrogen features that were blobs in Hubble's images now snap into focus, telling stories of formation and collision we could only guess at before. The secret lies in JWST golden, segmented mirrors and its perch a million miles from Earth, far beyond our atmosphere's distorting blur. While Hubble observed mainly invisible and ultraviolet light, JWST specializes in infrared, the wavelength range where the oldest light arrives after eons of stretching across expanding space. It's like tuning a radio to a frequency Hubble couldn't access, picking up whispers from the universe's infancy. Some of JWST's most distant captures show galaxies as they existed just 200 million years after the Big Bang. So early, their stars hadn't yet polluted space with heavy elements. These aren't just galaxies, they're cosmic fossils preserving the moment the first stellar fires ignited. But JWST's real power isn't just in seeing farther, it's in measuring with unprecedented precision. Spectroscopy, the art of splitting light into its component colors, reveals the chemical fingerprints of these ancient galaxies. Hubble could do this for a handful of bright targets. JWST handles hundreds simultaneously, with enough sensitivity to detect the composition of atmospheres on exoplanets 1,000 light-years away. Every spectral line is a clue: oxygen levels, star formation rates, even the velocity of gas swirling around supermassive black holes in galaxies that existed before Earth formed. The implications are already rewriting textbooks. Some of JWST's early discoveries suggest early galaxies grew faster and larger than models predicted, posing fresh challenges to our understanding of cosmic dawn. Others reveal galaxies so old they shouldn't exist under standard cosmology, celestial Methuselahs that force us to reconsider how structure emerged in the young universe. With each observation, JWST isn't just adding data. It's testing the boundaries of physics itself, probing whether dark matter behaves as we think, or if inflation left traces in galaxy distribution we've only now become equipped to see. And this is just the beginning. JWST mission will span years, peering deeper into the infrared frontier with every pointing. Where Hubble gave us snapshots, JWST delivers a high-definition movie of cosmic evolution, frame by painstaking frame. The night sky will never look the same, not because it's changed, but because we've finally grown eyes sharp enough to see what was always there, hidden in the redshifted dark. Here's an eerie thought: the universe still carries the reverberations of its own birth. Long before galaxies or stars existed, sound waves rippled through the primordial plasma of the young cosmos, compressing and expanding matter in rhythmic pulses. These weren't ordinary sound waves, they moved at nearly half the speed of light, their peaks and troughs imprinting a cosmic fingerprint that astronomers now use as one of the most precise rulers in existence. We call it the sound horizon, a fossilized echo from the Big Bang, frozen in time when the universe was just 380,000 years old. Picture the early universe as a seething ocean of superheated particles, protons, electrons, and photons colliding furiously in a dense, glowing fog. In that chaos, gravity pulled matter toward denser regions while radiation pressure pushed it away, creating oscillations that propagated like sound through water. These pressure waves traveled a fixed distance about 500,000 light-years before the universe cooled enough for atoms to form, abruptly silencing the cosmic symphony. That distance became the sound horizon, a standard ruler etched into the distribution of matter. Today, when astronomers map millions of galaxies, they find a curious pattern. Galaxies are slightly more likely to be separated by this exact scale than any other distance. It's as if the cosmos has a hidden grid with galaxy clusters spaced at intervals matching those primordial sound waves. Imagine dropping pebbles into a pond, then freezing the water mid-ripple. The rings would forever mark where the waves once traveled. The universe did exactly that, but on a scale so vast, the ripples span hundreds of millions of light-years. Scientists measure these baryon acoustic oscillations, BOs for short, by comparing the expected size of the sound horizon to how stretched it appears in galaxy surveys. The more space has expanded since the waves froze, the farther apart the galaxy pairs appear. It's like measuring the stretch marks on a balloon to calculate how much it's been inflated. The Planck satellite's cosmic microwave background maps give us the original, uninflated size, while galaxy surveys like the Sloan Digital Sky Survey show the stretched version today. What's astonishing is how precise this cosmic ruler is. The sound horizon scale has been calculated to within 1% accuracy, a measurement so fine it's like determining the width of a human hair from 10 miles away. By comparing BO data across different cosmic epochs, astronomers have reconstructed the universe's expansion history with unprecedented clarity. The results consistently confirm dark energy's accelerating push, showing how its influence has grown over billions of years. Even more mind-bending, we've reconstructed those primordial sound waves as actual audio. Using data from the cosmic microwave background, scientists converted the density fluctuations into sound frequencies our ears can hear, a deep, rumbling drone that swells and fades like the breath of the cosmos itself. Listening to it is like eavesdropping on the universe's first vibrations, a sonic relic from a time when space was 1,000 times hotter and denser than the core of the sun. Yet BOs aren't just about the past, they're helping unravel the Hubble tension. When combined with supernova and CMB data, they provide an independent cross-check on expansion rates, adding weight to the discrepancy between early and modern universe measurements. Some theorists speculate that unknown physics during the universe's adolescence, perhaps an early burst of dark energy, might have subtly altered the sound horizon's apparent size, skewing our calculations. Others see it as evidence for exotic particles or modified gravity. Every galaxy map, every acoustic oscillation is a ripple across time, a whisper from an era when the universe was a hellish plasma storm, ringing with sound waves that would one day become the yardstick by which we measure the fate of everything. The cosmos doesn't just expand, it sings, and in its echoes we find the rhythm of creation itself. Some stars wear their hearts on their sleeves, or rather, in their light. Cepheid variables, a special class of pulsating stars, throb with rhythmic precision, brightening and dimming like celestial metronomes. What makes them extraordinary isn't just their pulse, but the secret message encoded in their flicker. The brighter the Cepheid, the slower its heartbeat. This seemingly simple relationship, discovered by Henrietta Swan Leavitt in 1912, unlocked the cosmos scale, turning these stars into the universe's most reliable yardsticks. Picture a Cepheid cycle. Over days or weeks, it swells like a breathing lung, its outer layers heating and expanding, then cooling and contracting. As it grows larger, its surface temperature drops slightly, glowing yellower and dimmer. Then the reverse, shrinking, heating, and blazing brighter in a blue-white peak. This oscillation isn't random. It's a precise dance between radiation pressure and gravity, with the star's helium layer acting as a cosmic piston. A typical Cepheid might swing from 5,000 to 10,000 times the sun's luminosity, its brightness curve tracing a smooth, predictable wave. Leavitt's genius was noticing a pattern in the Magellanic Clouds. The longer a Cepheid's pulsation period, anywhere from 1 to 100 days, the more luminous it was. Think of it like a lighthouse. Slower flashes mean a more powerful beacon. Since all these stars were roughly the same distance away, their apparent brightness differences reflected true luminosity variations. This period luminosity relationship became astronomy's Rosetta Stone. Measure a Cepheid's pulse rate and you know its true brightness. Compare that to how dim it appears from Earth and you've calculated its distance with stunning accuracy. Hubble leaned on this tool when proving Andromeda wasn't a nebula but a galaxy far beyond the Milky Way. Modern astronomers wield it with even greater precision. Space telescopes like Hubble and JWST monitor Cepheids in galaxies up to 100 million light-years away, their cameras capturing brightness changes as small as 1%. The process is meticulous. Observe the star for weeks, plot its light curve, time its pulses, then consult Leavitt's law to reveal its luminosity. The dimmer it appears compared to this baseline, the farther away it must be. But Cepheids aren't solo acts, they're the first rung on the cosmic distance ladder. By anchoring them in nearby galaxies with parallax measurements, tracking how their positions shift as Earth orbits the Sun, astronomers calibrate their absolute brightness. These calibrated Cepheids then measure distances to galaxies hosting Type 1, a supernova, whose uniform explosions become visible across billions of light-years. It's a chain of cosmic stepping stones, each verifying the next, stretching our reach ever deeper into space. The stakes couldn't be higher. When the Hubble Space Telescope pinned down Cepheid distances to 70 galaxies in the 1990s, it revealed the universe's expansion rate with unprecedented precision and set the stage for discovering dark energy. Yet even these stellar workhorses have quirks. Metallicity, the abundance of elements heavier than hydrogen and helium, can subtly tweak a Cepheid's pulse. Dust between stars dims their light, requiring careful correction. That's why JWST infrared eyes are game changers, peering through dust clouds to study Cepheids in crystal clarity, refining our cosmic measurements to razor's edge accuracy. Every flicker of a Cepheid is a heartbeat echoing across space-time, a pulse that helps us measure not just where we are, but how fast the universe is stretching beneath our feet. Without these stellar lighthouses, the cosmos would still be a vast, uncharted ocean, their rhythmic glow the first true map of the dark. The universe is supposed to play fair, expanding evenly in all directions, with no favorite spots or privileged viewpoints. This idea, called the cosmological principle, is baked into nearly every equation describing cosmic evolution. But scattered across the heavens are structures so enormous they strain this assumption to the breaking point. Take the Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years end to end. A bristling superhighway of matter so vast, light would need 3/4 of the universe's current age just to traverse it. If expansion were truly uniform, how could such a behemoth hold itself together against the relentless stretching of space? Maps of the cosmic web reveal this isn't an isolated case. Galaxy surveys uncover filaments and walls like the Sloan Great Wall or the recently discovered South Pole Wall, threading the cosmos on scales exceeding 600 million light-years. These aren't random clumps, they're the skeletal remains of density fluctuations from the Big Bang, regions where gravity temporarily outmuscled expansion. The sheer size of these structures raises an unsettling question: what if dark energy doesn't push everywhere equally? Could pockets of the universe resist acceleration more fiercely than others, leaving behind these titanic fossils? The cosmological principle insists the universe should look roughly the same no matter where you stand, a premise backed by the cosmic microwave background's near-perfect uniformity. Yet the Hercules corona wall defies this expectation, its existence implying matter clustered on scales that shouldn't be possible under standard models. Some theorists propose these are illusions of perspective, that what we perceive as connected structures are actually chance alignments of smaller clusters along our line of sight. Others suggest more radical ideas. Perhaps dark energy's repulsive force varies across space, weaker in some regions where matter clumps defiantly hold their ground. To test these theories, astronomers turn to redshift surveys like the Sloan Digital Sky Survey, which maps millions of galaxies in 3 dimensions. By tracing the distribution of matter across billions of light years, these projects reveal whether megastructures are statistical flukes or evidence of deeper cosmic unevenness. Early results are ambiguous. While most large-scale structures align with cosmological models, outliers like the Hercules corona wall linger like unanswerable riddles. Future instruments like the Euclid Space Telescope will probe even wider swaths of the universe, searching for cracks in the cosmological principle's foundation. What's at stake isn't just academic. If expansion isn't uniform, it could explain discrepancies in the Hubble constant. Variations in local versus global measurements might reflect genuine regional differences in how fast space stretches. Imagine a loaf of raisin bread rising unevenly in the oven, with some sections inflating faster than others. Galaxies in slower expanding zones would appear to recede more sluggishly, skewing our cosmic calculations. The Hercules corona wall might be more than a curiosity. It could be a signpost pointing toward a universe far lumpier and more unpredictable than we ever imagined. The universe plays tricks with time, especially when you're watching a star die from across billions of light years. Take 2 supernovae, one erupting in a nearby galaxy, the other in the early universe. Film them side by side and you'll notice something bizarre. The distant explosion unfolds in slow motion, its brightening and fading stretched like a record played at the wrong speed. This isn't a camera glitch or an optical illusion. It's direct evidence that space-time itself stretches, warping time as it expands. Here's how it works. When a massive star collapses, it unleashes a supernova, a brilliant fireball that brightens over days or weeks before gradually dimming. Nearby, we see this play out in real time. But for ancient supernova, their light must traverse an expanding universe. As space stretches during its journey, the light's wavelengths elongate redshift, and crucially, the intervals between photons also stretch. That means the entire event appears dilated, like a cosmic rubber band pulling apart the fabric of time itself. A supernova that brightens and fades in 20 days locally might take 40 days when observed from the universe's infancy. The effect, called cosmological time dilation, was first confirmed in 2001 using Type 1, a supernova. Researchers compared light curves graphs of brightness over time from nearby and distant explosions. The distant supernova didn't just look dimmer, their entire life cycle was systematically slower, like comparing a hummingbird's wing beat to an eagle's. The degree of slowdown precisely matched predictions from Einstein's relativity, where expanding space literally stretches the duration of events happening within it. Picture a photon leaving a supernova 13 billion years ago. At that moment, the universe was far denser, with space compressed. As the photon travels, the cosmos expands beneath it, forcing the photon to climb an ever-steepening hill. The closer it gets to us, the more stretched its energy becomes, and the longer the gaps between its arrivals. It's akin to running on a treadmill that's gradually speeding up. Your strides lengthen, and your movements seem drawn out to an outside observer. This time warp isn't just a curiosity, it's a tool. By measuring how much supernova light curves are stretched, astronomers can independently verify cosmic expansion rates. The amount of time dilation directly correlates with redshift. The greater the stretch, the farther and older the supernova. Recent studies even use machine learning to analyze these slowed explosions, extracting precise expansion history from their elongated profiles. And there's a haunting implication. If we could witness the earliest moments of the universe in extreme slow motion, the frantic chaos of the Big Bang's first seconds might appear to us as a languid, almost glacial unfolding. Time itself was compressed then, just as space was. The universe's clock ticks differently depending on when and where you're watching from. Every slowed supernova is a reminder the cosmos doesn't just stretch space. It stretches reality. Dark matter is the universe's silent anchor, an invisible giant whose gravitational grip holds galaxies together even as dark energy tries to rip them apart. Picture a cosmic tug-of-war where dark energy stretches space like an endless rubber band, while dark matter pulls back with the steady heft of a hidden titan. Between them, caught in the middle, swings the rope, the visible universe, stars, gas, and everything we can see with our telescopes. Without dark matter's counterbalance, galaxies would have been shredded eons ago, their stars scattered into the void by dark energy's relentless push. We've known about dark matter's existence since the 1930s, when astronomer Fritz Zwicky noticed galaxies in the Coma cluster orbiting so fast they should have flown apart unless some unseen mass was holding them together. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars on the outer edges whirled just as fast as those near the center, defying Newton's laws unless an invisible halo of matter enveloped each galaxy, adding extra gravitational glue. Today, we know dark matter outweighs visible matter 5-to-1, its gravitational tendrils weaving a vast cosmic web that guides where galaxies form and how they cluster. But here's the twist. While dark matter's pull shaped the universe's structure, dark energy is writing its future. Imagine two teams in that cosmic tug-of-war. Dark matter's side is strong but static, its gravitational muscles fixed in quantity. Dark energy's side, however, grows stronger as space expands, its repulsive force multiplying with every new inch of vacuum created. For billions of years, dark matter dominated, slowing expansion as galaxies clumped along its invisible scaffolding. Then, around 5 billion years ago, dark energy took the lead and the universe's stretching began to accelerate. This battle leaves visible matter as the rope, stretched but not yet broken. Galaxies within clusters, bound by dark matter's grip, resist being torn apart, but the space between clusters grows emptier and more isolated as dark energies push out muscles gravity's pull over cosmic distances. The Virgo supercluster, home to our Milky Way, will remain intact, but distant galaxy clusters will one day vanish beyond an unreachable horizon, their light stretched too far to ever reach us. What's fascinating is how delicately balanced this contest has been. If dark matter were slightly weaker, galaxies would never have formed in the first place. If dark energy were stronger, it would have ripped apart proto-galaxies before stars could ignite. The fact that we exist to ponder this tug-of-war hints at a universe fine-tuned on a knife's edge, a cosmic game of strength where the competitors' forces align just precisely enough to allow galaxies, planets, and life to emerge. Yet mysteries linger. Why does dark matter interact only through gravity, ignoring light and matter? Could it decay or transform over time, subtly altering the contest? Telescopes like Euclid and the Vera Rubin Observatory are mapping dark matter's distribution in unprecedented detail, searching for clues in the bending of starlight and the motions of galaxies. Each observation sharpens our understanding of this invisible architect and its enduring struggle against the vacuum's strange, accelerating push. The cosmos isn't just expanding, it's a battleground between two unseen giants with the fate of everything hanging in the balance. The night sky as we know it is about to get a revolutionary upgrade, one that could finally crack the Hubble tension wide open. In the high deserts of Chile, engineers are putting the finishing touches on the Vera Rubin Observatory, a telescope with a camera so massive it could photograph a golf ball on the moon. Scheduled to see first light in 2025, this behemoth won't just observe the cosmos, it will devour it whole, scanning the entire southern sky every 3 nights with its 3.2 billion pixel eye. Imagine a time lapse of the universe on steroids, where every frame captures 10 million galaxies, a million moving asteroids, and thousands of exploding stars. Its primary mission, the legacy survey of space and time, will run for a decade, creating the most detailed movie of cosmic expansion ever made, Rubin's secret weapon. A dance of mirrors and sensors so precise, it can detect the faintest flickers from objects 18 billion times dimmer than the human eye can see. Unlike traditional telescopes that focus on single targets, Rubin's wide-field design lets it catch fleeting events, supernova, merging neutron stars, even interstellar comets as they happen. But here's the real prize. By mapping billions of galaxies and their distortions from weak gravitational lensing, Rubin will trace dark matter's hidden scaffolding in unprecedented detail. Every warped galaxy image is a breadcrumb leading back to the invisible mass bending its light. Combined with supernova data, this could settle the debate over whether dark energy's strength varies across cosmic time. Meanwhile, orbiting 1 million miles from Earth, the European Space Agency's Euclid spacecraft is already rewriting the rules of cosmic cartography. Launched in 2023, this infrared explorer isn't just another space telescope. It's a dark energy detective armed with 2 cutting-edge instruments. Its visible light camera, capable of spotting galaxies 10 billion light-years away, works in tandem with a near-infrared spectrometer that dissects their light into rainbow-like spectra. Together, they'll construct a 3-dimensional map of 35,000 square degrees of sky, measuring the shapes and redshifts of over 1 billion galaxies. Picture a CT scan of the universe's large-scale structure, with Euclid's gaze piercing through cosmic dust to reveal the skeleton beneath. Where Rubin excels in volume and speed, Euclid specializes in precision. Its razor-sharp optics can measure galaxy shapes so accurately, it detects distortions smaller than 1%, crucial for studying how dark energy alters the growth of cosmic structures over time. But the real showstopper is Euclid's ability to probe baryon acoustic oscillations, those frozen sound waves from the early universe across 9/10 of cosmic history. By comparing these ancient ripples to their modern equivalents, scientists hope to spot subtle changes in expansion rates that could explain the Hubble tension. The synergy between these projects is what makes this era golden. Rubin's torrent of real-time data will flag mysterious phenomena for Euclid's deeper scrutiny, while Euclid's ultra-precise distance measurements anchor Rubin's wider but coarser maps. It's like having both a high-speed surveillance camera and a forensic microscope pointed at the cosmos simultaneously. Early simulations suggest their combined power could shrink uncertainties in the Hubble constant by a factor of 5, potentially exposing whether the discrepancy stems from measurement errors, new physics, or something even wilder, like a flaw in our understanding of gravity itself. Concept art of these missions in action looks like something from a sci-fi epic. Rubin's dome, perched on Cerro Pachon, rotates beneath star-streaked skies as its camera gulps down 15 terabytes of data nightly, enough to fill 3,400 DVDs every 24 hours. Euclid, floating at Lagrange point 2, unfolds a sunshield the size of a tennis court to keep its instruments at -150 degrees Celsius, their sensors drinking in infrared whispers from the edge of time. Together, they represent humanity's most ambitious attempt yet to interrogate the universe's accelerating expansion, not with a single snapshot, but with a decade-long interrogation of light, space, and time. What they find could rewrite textbooks. If dark energy's push is truly constant, the tension may resolve into a consensus. But if these instruments uncover evidence that expansion rates vary by era or direction, it would ignite a firestorm in cosmology. Perhaps the universe isn't just expanding, it's unraveling in ways we've barely begun to imagine. With Rubin and Euclid leading the charge, we're not just observers of the cosmos anymore. We're detectives piecing together clues to the greatest mystery of all, why everything is flying apart and what that means for the fate of us all. The universe's final curtain call won't be dramatic, no fiery explosions, no grand collapse. Instead, the most likely scenario is a slow, silent fade into darkness, a fate cosmologists call heat death. Picture an endless, featureless void where the last dying stars have burned out. Black holes have evaporated, and even the protons that once built galaxies have decayed into faint, scattered particles. Temperatures hover just a whisper above absolute zero, and time itself becomes meaningless in a cosmos where nothing happens, not just for years or eons, but forever. This bleak outcome isn't science fiction. It's the inescapable consequence of entropy's relentless climb, the universe exhausting every drop of usable energy until even motion ceases. But heat death isn't the only possibility. Dark energy's grip could tighten so severely that it shreds the fabric of reality itself, the Big Rip. If dark energy evolves into phantom energy, growing stronger as space expands, it would eventually overpower every force holding matter together. Galaxies, stars, even atoms would be torn apart in a crescendo of destruction, leaving behind a fragmented cosmos where no two particles can ever interact again. The timeline here is apocalyptic. 60 million years before the end, galaxy clusters disintegrate. Months prior, stars explode as space rips them from within. In the final moments, atomic nuclei are shredded into quark soup, and the universe becomes a foam of isolated, disconnected voids, which fate is more probable. Current data slightly favors heat death, with dark energy behaving as a constant force rather than the runaway phantom energy the Big Rip requires. Observations of supernova and baryon acoustic oscillations suggest dark energy's strength has remained stable for billions of years, making a gradual fade more likely than a violent end. But the margin is slim. Even a tiny upward creep in dark energy's strength over time could tip the scales toward the rip. It's like balancing a pencil on its tip, seemingly stable until an imperceptible nudge sends it crashing. Zoom out for a moment to grasp the enormity. Earth, a pale blue dot orbiting an unremarkable star, sits in a galaxy that itself is just one of 2 trillion in the observable universe. Those galaxies are racing apart, their light stretching into invisibility as space's expansion outpaces the speed of light itself. In 1 trillion years, any civilizations born too late will see only blackness. No evidence of the Big Bang, no hint of other galaxies, just an eternal void. The cosmos won't so much end as forget itself, its history erased by the very expansion that once gave it life. Yet this cosmic loneliness carries a strange beauty. Every star that ever burned, every planet that nurtured life, was borrowing energy from a universe destined to cool and fade. Our existence is a flicker in the darkest of nights, a fleeting spark against the infinite dark. But for now, the universe is still young enough to wonder, to reach outward, to trace the contours of its own inevitable end, and in that act of discovery, defy the silence to come. Let's take a moment to absorb the sheer audacity of what we've uncovered. The universe isn't just expanding, it's accelerating, as if some invisible hand has pressed down on the cosmic gas pedal. Dark energy, that mysterious force driving this runaway expansion, isn't just a minor player. It dominates the cosmos, making up nearly 70% of all energy in existence. Think about that. The stuff we can see, stars, galaxies, planets, is a mere 5% of the total cosmic budget. The rest, a shadowy realm of dark matter and dark energy, pulling and pushing the universe in ways we're only beginning to grasp. Perhaps even more mind-bending is the Hubble tension, the stubborn disagreement between how fast the universe is expanding now versus what the early universe's afterglow predicts. It's as if the cosmos left us two conflicting blueprints, and astronomers are scrambling to figure out which one, if either, is correct. Could there be unknown physics at play? A flaw in our measurements, or something even more extraordinary lurking in the gaps? And then there's the fate of it all. Depending on dark energy's whims, we could be heading toward a slow, cold fade into heat death, or a catastrophic big rip where even atoms are torn apart in the final moments. The fact that we're here to ponder these questions at all is a cosmic miracle, a fleeting window in time where the universe is old enough to understand itself, but young enough that its mysteries are still within reach. So tell us, what staggered you the most? Was it the way empty space itself might hold the key to dark energy, the ghostly pull of neutrinos quietly shaping expansion, or the eerie possibility that future civilizations will gaze into an empty sky, unaware of the cosmic drama that once played out beyond their horizon? Drop your thoughts in the comments, and if you're hungry for more mind-bending explorations of the cosmos, hit subscribe. The universe is full of mysteries. Let's unravel them together.